So in this video, we're going to start learning about roots and how to simplify roots. It's going to be simply more than just typing in a calculator. So your objective is that you can state the vocabulary dealing with roots, and then you can simplify it nth root using factor trees. So there are two types of numbers. There are irrational numbers and rational numbers. Irrational numbers are numbers that cannot be written as a fraction, versus rational numbers are numbers that can be written as a fraction. I like to think if you're like a rational person, you kind of have your head on straight, so they're kind of nice and clean, where your irrational person is kind of all over the place, which they can't be written as a fraction. That's kind of how I keep the two straight. So our irrational number are non-repeating decimals. Well, the most famous non-repeating decimal is the number pi, which is 3.14159, so forth, blah, blah, blah. It keeps going on forever, and people have dedicated their life trying to find all the digits of pi. Another irrational number would be any decimal that goes on forever. And the way we get those decimals are from roots. Roots, anytime I take a square root of a number that is not a perfect square, kind of going on your vocab, are numbers squared, whatever it equals. So 1 squared is 1, so 1's a perfect square. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. So all these numbers, and we can keep going on forever and ever, are perfect squares. 3 is not a perfect square. Nothing squared is 3. So if you would type this in your calculator, you would get 1 point something, and it would go on for a long time. And your calculator would stop at a certain digit, but it keeps going because there's no repeating or repetition between those numbers. Where a rational number are just any number that can be written as fractions. So they are fractions. But as decimals, they're just any decimals that terminates, that stops. It's like 0.25. Or repeats, like 0.3 repeating. All these numbers can be written as fractions. Or all your integers. Your integers are just your nice numbers, positive or negative, like -5, 10, 0, 1,000. These are all integers, and these are all rational numbers. Roots is when the radicand is a perfect square. So if I have the square root of 49, well, square root of 49 simplifies down to be 7. 7 times 7 is 49, or 7 squared is 49. So therefore, this is a rational number where 3 is not. So it looks like it could be irrational, but when you simplify, it actually is. So let's review, and this kind of goes with our previous 3 videos. 6 squared means 6 times 6, so this is 36. -14 squared is -14 times -14. Negative times negative is positive, so that's 196. -9 squared is 9 times 9. And the way you want to think of this, you're only squaring 9. Notice this one, the whole thing was in parentheses, so it was -14 squared. This one is saying you have a negative, or -1, times 9, which is -81. So how can I undo this? How can I reverse squaring a number? So you're undoing. Well, that is where roots come into play. A root, which the most famous root you're probably familiar with, is a square root, which looks like that. This undoes a square. Alright, so what it means to undo a square, if I have 4 squared, and I took the square root, 4 squared is 16, square root of 16 is 4. They simply cancel each other out. And I can reverse it. I can go the square root of 4 is squaring that. Well, square root of 4 is 2. 2 squared is 4. They're inverses of each other. Just like adding and subtracting are inverses of each other, and so are multiplying and dividing. Alright, so radicans, they're also referred to as roots. So I might use or radicals. I might use radicals or roots. They mean the same thing. And the way we kind of look at roots is what times itself, index number of times, equals the radicand. Because we can have different kinds of roots. There's cube roots, fourth roots, fifth roots. You can have roots all the way up. It doesn't matter the number. Well, we get the number from the index, and the index is the number that goes right into the little bend of the root. So this one has an index of 3. The number inside is called the radicand, and then you have the radical symbol. So what it means, if I want to try to figure this out in my head, I have to go, okay, what times itself 3 times gives me 8. Well, you know it's going to have to be less than 8, and it turns out 2 times 2 times 2 is 8. So the cube root, is how we pronounce this, of 8 equals 2. And I can do the same thing for a square root. If I want to do the square root of 36, I have to go what times itself equals 36. Well, that is 6 times 6. So square root of 36 is 6. Or you can think of it as 6 squared is 6. So let's take a look at square roots in more detail. A lot of students, if they see the square root of 25, they think there is one answer. However, they are wrong. There's actually 2 in most cases. So you have to think to yourself, what times itself is 25? And right away, students will be like, oh, it's 5. 5 times 5 is 25. So 5 is one answer. However, there is one more set of pair numbers that are the same that equal 25. And you might be sitting there thinking, well, 5 times 5 is the only ones that equal. However, 2 negatives make a positive. You've learned that for a while ago. Well, negative 5 times negative 5 are the same. So negative 5 is also an answer, or we rate it as plus or minus 5, meaning the positive and negative answer is 5. So when you take a root of a positive number, most of the time there are 2 answers. The exceptions is the square root of 0. The only way to get the square root of 0 is 0. There's no positive or negative 0. Or if you have a negative number. So say if I have negative 25. So you have to think to yourself, what 2 numbers multiply together to be negative 25? And you can be here the rest of your life trying to find this pair, because 5 times 5 is 25, but to get a negative, one has to be negative and the other one has to be positive. These are not the same. So therefore, there is no real solution. You cannot take a square root of a negative number. If you do it in your calculator will give you an error, say a math error or domain error, because it's impossible. So we're going to be looking at simplest radical form for square roots, and we're actually going to look at cube roots and fourth roots with this section. So the way we work with simplest radical form is that there's no perfect squares or combination of perfect squares under the radicand. So that's the one we're going to be focusing on today. Getting those perfect squares out, just like the square root of 25 is 5. We can't just leave it as square root of 25. There's no radicals in the denominator or roots in the denominator. That will be on the 4th video. And there's no fraction of decimals under the square root. And again, we'll be dealing with that in the 4th video. Alright, to simplify this expression, I'm going to give you a little analogy. Notice up here I have a little root with a jail. Now, breaking out of jail is not very easy because more and more people would probably do it because they don't want to be locked up for long periods of time. Some people succeed. Well, for you to break out of jail, break out of the root, you need a pair. A pair of you need to break out. So when you break out, then you're allowed to go on the outside. If there is only one of you, then you're not allowed to break out. So you need a pair to break out of the jail. Or another analogy I use, if you're inside, for you to go play outside, So outside the radical, you need a friend, and you only can really have one friend. You can't have 3 friends. And again here, like, you only get a pair. If there's 3 of you, 1 has to be left behind. 3 would just, you need a pair to go break outside the jail. So let me show you what I'm talking about. So to use this, we're going to do factor trees. And hopefully you're familiar. So factor trees is you go, what times itself is 90? Well, that's 9 and 10. And then 9 is 3 and 3. 10 is 2 and 5. You go until you have prime numbers. Well, 3 is prime, so I circle them, and 2 and 5 are also prime. So again, for you to break out of jail, to break out of this radical, you need a pair. Well, I have a pair of 3s. So 3 is left on the outside. If you do not have a pair, I only have 1, 2, and 1, 5. They need to stay inside. And the operation is always multiplication. So it's 2 times 5, which just gives you 3 square root of 10. So on B, I have 192. So I need to do my factor tree. Again, it doesn't matter how you start. I know 3 divides this. So that is 64. 3 is prime, so I'm going to circle it. 64, I know it's 8 and 8. 4 and 2. 2 is prime, 4 is not, because I can go 2 times 2. Again, I like to circle because it helps me keep track of what numbers I have. I have 4 and 2, and 2 and 2. Alright, so I need a pair to break outside. I have 1 pairs of 2s. So 1 2 gets to go outside, breaks out of jail. I have 2 pairs of 2. And then I have another one. So 3 2s get to go outside since there's 3 pairs of 2. The 3 does not have anyone to help them. So 3 has to stay inside the radical, or inside the jail. And then I multiply everything out. 2 times 2 times 2. They're on the outside, so that's 8 square root of 3. So on C, I have the square root of 75. Well, 75 is 3 and 25. And that is 5 and 5. Circle my primes. I have a pair of 5, so 5 gets to break out. 3 needs to stay in. Square root of 125, that's 5 and 25. And 5 and 5. Well, I have a pair of 5s, so 1 5 has to stay, but can't have 3 of them, only 2, so that extra 5 has to stay in. And then we have expressions with variables. So here I have 16. Now some of you, if you brought your A game, square root of 16 is 4, so you know 4 goes out. Or if you did it by the factor tree, you would get the same thing. I have 2 sets of 2s, so that's 2 times 2. And then the A's, remember A cubed means A times A times A. So I have a pair of A's that go out. And then I have 1 A that stays in. I don't have any numbers to stay in, so that's 4A square root of A. Here, square root of x squared y to the 5th is x times x. Y to the 5th is y times y times y times y times y. So you have x's, you have a pair of y's, 2 pairs of y's. So that's an x times y square root of y. Because 1 y had to be left in. Well, y times y is y squared square root of y. Alright, so then we have something with nth roots, and nth roots are, besides square roots, we're going to deal with a cube root, which has the index of 3, and fourth root. And the only difference is going to be kind of the same strategy with square roots, but since in the index is 3, we need 3 to break out. On this one, we need 4 to break out. Otherwise, the same procedure is the same. We're still going to do factor trees. So let's do 2 of cubes, and we'll do 2 with fourth roots, and then we'll be done. So I have 80. So I'm still going to do my factor tree, 8 and 10. Break it down to 4 and 2, 2 and 2, 2 and 5. So these are all my primes. So I need 3, since my index is 3, to break out. So I have 1, 2 that goes out, and then I have a 2 and a 5 that got left in. So it's 3. So I'm left with 2 times 5 on the inside, and multiply that out to get 2 cube root of 10. So on B, break down 81, which is 9 and 9. 3, 3, 3 and 3. I have 5 p's and 3 q's. Alright, so I have one set of 3's because I have 3 of them, but 1 3 has to be left in. I have one set of p's, so 1 p gets to go out, but 2 p's have to be stayed in, so that's p squared. And then all my q's, because I have exactly 3 of them, get to go out. Alright, and then fourth root's very similar concept. 64 is 8 and 8, which is 4 and 2, 2 and 2, 4 and 2, 2 and 2. Alright, so I'm going to find, I need 4 2's. So 1, 2, 3, 4. So 1, 2 gets to go out, but 2 of them got left behind, so that's 2 times 2, which is 4. And then on my last example, 324, I need to break that down. I know 4 and 81. This is 2 and 2. 81 is 9 and 9. 3 and 3. Alright. So I have the fourth root. I need 4 to go outside. Well, I have 4 3, so a 3 gets to go outside, and 2 2, so a 4 stays in. And then I have my variables. I have 6 m's. I have 5 n's, and I kind of like to group them in groups of 4 because then it helps me keep track. And 12 p's. So that's 1 set, 2 sets, and 3 sets. Alright, so to join here, I have 1 m, 1 n, and actually 3 p's. So p times p times p is p cubed. So I have m, n, p cubed. And who got left? I have 2 m's that got left inside, and then 1 n. Alright, so review. Make sure you know the difference between rational and irrational. We'll be talking more and more about that. Your square roots, your simplest radical form, which we'll work on more, and then your nth roots. And really kind of remember that analogy. We'll be using this a lot. Reminder to do reflections. You get credit for watching this video.